All right. Thank you very much. It's a pleasure to be here. I'll be talking about how Keck time through the NASA allocation has been really instrumental in helping us understand the transient infrared sky and teaching us completely new regimes when it comes to massive stellar death. And in particular, what I want to start with, I think I don't have to convince this audience that black holes exist. There are stellar mass black holes that we know of. And the question I want to start with is this very fundamental question of what stars form black holes? What types of stars turn into black holes? And if you looked at the state of the field about 20 years ago, this is a figure that summarizes the state from a review article. If you plot the mass of a star against its metallicity, there are these islands of regions where we think stars explode and where they don't. So roughly about 8 to 20 solar masses, we think stars explode and turn into neutron stars. But as you go to more massive stars, around 20, 25 solar masses, the picture, mostly theoretical, was that these stars fail to explode and probably turn into black holes. All theoretical again. But if you look at the state of the field today, based on more modern numerical calculations, it's much more complicated than that. It looks more like this, where instead of getting these clean islands of explodability, you get these picket fence. And where the black holes land in this picket fence, in this mass diagram, depends very much on the calculation you're doing and the assumptions that you're making. And the reason it's so complicated because there are simply no observational constraints on what stars turn into black holes. So why is it so difficult to make this connection? And to understand that, I'd just like to talk a bit more about what does it mean that a star fails to explode and turns into a black hole. The general picture that we should be thinking of is something like this, where you have a massive star that towards the end of its life turns into a red supergiant. And at the end of its life, instead of exploding, the core implodes into a black hole. And the mass loss that happens because of the neutrino loss can eject some of the outer layers of the star, but most of it essentially falls back in forming a black hole. And by the end of it, what you get is a rapidly accreting black hole that's gobbling up its host star. And there is some amount of mass that is ejected that likely produces a very long-lived red transient that we can find. So as you can imagine, what you have to do to look for stars like these is look for disappearing stars instead of exploding stars. And it's remarkably difficult because you have to look for individual stars disappearing. So the only way, the large binocular telescope actually did a survey to look for these types of stars. And there's one really promising candidate that's known. What you see here is a star in the galaxy NGC 6946, before and after. It's a red supergiant in that galaxy that essentially disappeared over the course of a decade. And because of the coverage from the LBT survey, you can create a light curve of what it did before it disappeared. And it kind of looks like this. It stayed constant, remarkably constant for a year, for a decade, before it showed this faint red outburst and then disappeared. And there's a long-lived infrared afterglow that remains. And there's some debate about what exactly this is, but I'll come back to that in a bit. But in order to really find more of these, make this connection of where this picket fence is, where the black holes land, you really have to find more of these. And given that it's remarkably difficult to do from individual stars, what we've been trying to do is to look for these infrared brightenings and look for infrared brightenings in nearby galaxies. So this brings me to the specific survey that we've been trying to do as a part of a bigger team, and I'm really grateful to my team for helping me execute this survey. The idea is that we've been using a very well-known survey. It's NEOWISE. It's been surveying the sky for 15 years now. It was rejuvenated as an asteroid hunting mission. But what it does essentially is that it has this orbit around the Earth where essentially it takes two images. It takes one image of the sky every 6 months in two filters, 3.4 and 4.6 microns. So you get one epoch of imaging every 6 months. And you've been doing this for the last 10 years, roughly. And historically, the approach has been that you stack these images, go deeper and deeper, but we sort of just, instead of adding them, we subtract them, look for things that change. But the idea is that these two images taken 10 years apart, you subtract the two, you see there are these point sources that stick out that you wouldn't otherwise see if you were not subtracting the images. And that sort of has led us to this sample of about 5 million infrared transients and variables that we've been systematically sifting through. And this data is going to be released very soon, so keep an eye out for that. But what we've also had is a systematic ground-based follow-up program using NASA Keck time to get spectra for some of the most luminous infrared outbursts we can see in the nearby galaxies. And this is where this story begins, where these are WISE images of the same part of the sky in a nearby galaxy. You see there is a source right in the center. If you subtract the 2, you see that it's changed in brightness by ever so little, brightened by a factor of 2, roughly. This is an archival K-band image of the same part of the galaxy. You see these same 3 stars. These are the same 3 stars. And I was like, okay, star was there. It did something in the infrared. Not exactly sure what it was. Let me go and take a NIRIS spectrum of it, because NIRIS covers the entire wavelength band, and we can actually get all the features we're interested in. And this is what it looked like in NIRIS. So I was observing at 3 in the morning. I was like, 1, 2, 1, 2. Where's the third one? So, sometimes like, I've observed on NIRIS so much, but I couldn't just see. I was like, maybe I'm going crazy at 3 in the morning. So that was where the story really begins. Like, the star wasn't there at all. So the discovery was made even before the first photons hit the spectrogram, essentially. So then you go a deep dive and try to understand what's going on. It's a nearby galaxy. There's really nice HST imaging of the galaxy. This is a star that you see. It's reasonably bright. You can see it. And when you go and dig into the archives, what you see is that it did something quite dramatic in the last decade. What was caught by my pipeline was this infrared brightening and then fading subsequently. But in the optical, it's essentially just plummeted, disappeared over the course of a decade. So much so that we have HST imaging from the last couple of years. The source is gone. You can't see this star entirely in the optical. There's something very faint in the near infrared we can see from Keck MOSFIRE imaging that we got subsequently. So what's going on? So to answer that question, you kind of take all of this together and you ask, what did the progenitor look like before it disappeared? This is what it looks like. You have HST and Spitzer imaging from about 10, 15 years ago. It looks like a very luminous supergiant with remarkable dust excess, which is essentially indicative of very strong mass loss that the star was undergoing before it disappeared. And the picture, sort of, I think of it is that you have a main sequence star. Given the luminosity, it was probably something like 20 solar masses before, when it was born. And towards the end of its life, it turns into a red supergiant and forms this intense mass loss shell that produces this dust shell around the star. And what exactly causes this is something that we can talk about. But the idea is that it's a yellow supergiant progenitor. It's not exactly a red supergiant, and we can confirm that based on its optical luminosity and colors. But the most likely explanation for what actually happened in this case is that the star died. The core plummeted into a black hole, and as the star collapsed into itself, as the black hole started accreting, what we expect is that the angular momentum in the outer shells of the stars prevent the star from falling back into the black hole, and that essentially prolongs the accretion process to the extent that it doesn't disappear over the course of a month, but instead disappears over the course of a decade, which is what we see in the data. And you can actually do that some actual numerical modeling. What you see here is luminosity as a function of time. Initially, it's fairly flat around the Eddington luminosity of the star, and then it plummets as the accretion rate onto the black hole drops. But the entire reason we are able to explain these data is because the only way to get that is if you have a star that was stripped of its outer layers. It's a yellow supergiant instead of a red supergiant, because a red supergiant would take too long to accrete onto the black hole. There's too much mass in the outer layers, and there's too much angular momentum to get rid of. And it turns out that a picture like this actually explains both this object and the previous object in NGC 6946. So that's, of course, I'm happy to talk in more detail. Please come talk to me if you're interested in understanding more of the modeling. But a related topic that's also come up, very relevant in this context is that, like I said, mass loss seems to be necessary to explain properties of objects like these, the black holes that we are finding in time domain surveys. So the question that we are also answering at the same time is, how prevalent is this type of pre-supernova intense mass loss? And we know intense mass loss is common in supernova progenitors, and that's because if you imagine what a star looks like that has undergone intense mass loss, is that you have a star that's about to die, you have this dense circumstellar medium that's around it, and when the supernova actually happens, this crashes into this nearby CSM, producing signatures that we can see in spectra of supernovae. The most common types, these are called the type 2N, 1B, and there's a zoo now that I can't keep track of anymore. But in addition to seeing these spectroscopic lines, you also see dust formation. The idea is that when you get these very dense layers of material, dust happens to form very efficiently in these layers. So instead of using optical spectroscopy, again, infrared emission turns out to be a very effective way to look for stars that have recently ejected a lot of CSM and then subsequently gone supernova. So of course, this only works, the optical spectroscopy only works if the material is really nearby. Imagine if you had a shell that was much further out like this. In this case, the supernova would take years to actually reach the shell that is there at a time when you're actually not even following it up with spectroscopy, because rarely do observers keep track of individual supernovae out to years or decades after the explosion. But with free infrared imaging, like the one that NeoWise provides, you can actually just use the infrared, the dust emission that comes in the infrared bands to look for the same types of interaction signatures. So this is, again, something that WISE is really good at. And here is an example of a WISE transient that appeared in a very nearby galaxy. It's about 180 megaparsecs away. Most of this work was led by Charlotte Myers, who's worked with me. She's an MIT undergrad. And when you look at objects like this, what you realize is that if you plot the luminosity in the infrared of this source compared to other types of supernovae, you see that it's essentially one of the most luminous infrared supernovae ever discovered, except it was never really flagged in optical searches because it was too faint in the optical. And when you flag things like this, we can go back and use Keck to get spectra of these things. And it turns out that yes, with late time spectroscopy, you can actually confirm that these show lines of broad emission lines of hydrogen, exactly of the kind you would expect from supernovae that are interacting with the CSM around them, except you are essentially independently finding them without any other optical trigger because they're forming dust and becoming bright in the infrared. So anyway, I'll quickly say that there's a full population of these events that show late time brightenings that we can discover in WISE. We quantify the rates of the order of 3 to 4%. And NeoWise and Keck together are really enabling new regimes in massive stellar death that we haven't seen before. So thank you.